Okay, so let's start. So we're again reviewing the basics of linear algebra, and we'll hopefully be done with that in this particular class. In the last class, we defined the determinant of an n by n matrix, and we looked at different ways of computing or determining the determinant of a given matrix. We defined it through this particular property of permutations. So we express the determinant as a sum of various terms, each of which involved the sign of a particular permutation. We summed over all possible permutations of the sign of the permutation times this product of terms. Correct? And we saw that this was essentially the same as the definition of the determinant using minors and cofactors that you've seen in your high school. But then, although that's a nice definition, it's not helpful to us when we want to actually compute it. In practice, when we want to compute the determinant of a large matrix, we instead use the following approach of first converting the matrix into the row reduced echelon form, keep track of how many what kind of operations you did in order to bring it to the row reduced echelon form. And using that, you get a polynomial time algorithm to compute the determinant of any n by n matrix. So, whereas the original definition involved n factorial many terms, and therefore has complexity at least n factorial, this particular approach of computing the determinant takes only polynomial time. And that is in fact how you would compute the determinant in practice. All right. So in today's class, we'll move to eigenvalues and eigenvectors and also define positive semi-definite and positive definite matrices. Okay, so let's recall, given an arbitrary matrix A, an n by n matrix A, we say that some particular real number, lambda, is said to be an eigenvalue of A. If lambda times some vector, or if A times some vector equals lambda times V, for some non-zero vector. So if this happens for some non-zero vector V, then we say that lambda is an eigenvalue and V is called an eigenvector. Right? And for a given eigenvalue, there can be multiple eigenvectors. Right? So the set of all eigenvalues is called the spectrum. Spectrum is the collection of, or the set of all eigenvalues of A. And how do you compute the eigenvalues of a given matrix? Yeah? Okay, and what is the characteristic equation? So you look at the following equation, determinant of A minus lambda I equal to 0. The left hand side turns out to be a polynomial in lambda, so you get a polynomial equation in terms of lambda. You solve this polynomial equation, the roots of this polynomial equation correspond to the eigenvalues. So the roots of the polynomial determinant of a minus lambda I, they give you the eigenvalues. Right. But so here's a question. Suppose I have an n by n matrix A. Will it always have n real eigenvalues? Yeah? Can be repeated. Okay. Again, my question is, can it have n real eigenvalues? Need not be, right? Because some of the roots might be complex. So it's not necessary that it have real eigenvalues. So in particular, you can't say that there exists even a single eigenvalue for a particular matrix. It is possible that a matrix has no real eigenvalues at all. All the eigenvalues could potentially be complex. And that's always something to keep in mind. Okay? Because we're ultimately interested in eigenvalues over the reals. Right? On the other hand, if we are okay with complex matrices, we're working with the complex field, then every matrix A has n complex eigenvalues. Any complex matrix A will have n complex eigenvalues. Some of them might be repeated. And the reason is simply because this determinant of A minus lambda I, this is a polynomial of degree n, and therefore will have n roots over the complex numbers. Right? But over the reals, the determinant of A minus lambda I need not have any real roots. Okay, so now that we have this, suppose we know how to compute. So let's see how do you compute the eigenvalues and the eigenvectors. To compute the eigenvalues, you just solve this particular polynomial equation, determinant of A minus lambda I equal to 0. But how do you compute the eigenvectors? Yeah, so you just take computing right. So how do you compute an eigenvector? Suppose you have a particular eigenvalue lambda I and you want to find all the eigenvectors corresponding to this eigenvalue. You simply look at A. So obviously any eigenvector should satisfy A times V equal to lambda I times V, or in other words A minus lambda I times V equal to 0. Right? So you just have a set of linear equations that you have to solve. Effectively, that just boils down to finding out the null space of a particular matrix. Correct? Okay, so let's maybe look at some quick examples. Yes, we've already answered this. Let's look at some quick examples. Very simple examples at first. Suppose I have the n by n matrix of all zeros. What are the eigenvalues? N zeros, 0 repeated n times. And what are the eigenvectors? So any non-zero vector is an eigenvector for this particular matrix. So in fact, eigenvectors is simply all of Rn. Sure, Rn minus 0. Okay. Let's consider another example. Let's take the following matrix. Fine. It's the set of all non-zero eigenvectors, I should say. So the eigenspace would effectively be the entire Rn. What about the all ones matrix? Yeah. Okay. So how many zeros? Two zeros. Right. So lambda 1 equal to 3, lambda 2 equal to 0, and lambda 3 equal to 0. And can you give me eigenvectors for each of these? Yeah. So for example, 1, 1, 1. What about 1 minus 1? 1 minus 2, 1. Okay. And 3. Give me two linearly independent. Can you find any two linearly? Yeah. 1, 1, 1 minus 1. Okay, 1, 1 minus 2. What about 1 minus 1, 0? That is also an eigenvector. So you can easily compute any set of linearly independent eigenvectors. Okay. So right. So given an arbitrary matrix A, an n by n matrix A, we'll say that it is diagonalizable if it's similar to a diagonal matrix. So in other words, a matrix A, n by n, is diagonalizable if we can find some matrix P such that A equal to P inverse dP. So this is an invertible matrix D diagonal such that A equal to P inverse DP. Right. Is every matrix diagonalizable? Need not be. What can happen? Yeah. Which one? Which entire row or column? Correct. Okay, if a matrix is singular, does it mean it's not diagonalizable? Can you give me an example of a matrix which is non-singular, which is singular, but it is diagonalizable? Yeah. The all zeros matrix is an example.
Sigma is diagonal.
Correct. I'm not talking about singular value decomposition doesn't mean diagonalizability, right? So every matrix has a singular value decomposition, but here I want A to be similar to a diagonal matrix, which means that there should be a P such that A equal to P inverse DP. Right? So what is a linear algebraic interpretation of diagonalizability? It says that I can find another basis. So A describes some linear transformation from Rn to itself. Right? So it's a linear transformation. So one special class of linear transformations is the set of all diagonal linear transformations. When I say that a matrix A is diagonalizable, it means that there is some change of basis. I can change the basis in some particular fashion such that the linear transformation is effectively a diagonal linear transformation in that particular basis. Okay, so now going back to the original question, not every matrix is diagonalizable. So what all can go wrong? Okay, I mean something even more fundamental, even before we go to that. What is the first requirement for diagonalizability? Again, we're looking at diagonalizability over R. Right? It's possible that you don't have n real eigenvalues. Correct? That's one fundamental thing that can go wrong. So the matrix A may not have n real what else can happen? Suppose that A has n real eigenvalues, they could be repeated, they could all be distinct. So if all the eigenvalues are distinct, real and distinct, is the matrix diagonalizable? It is, right? So if A has n distinct eigenvalues.
Sir, is it always the case that a matrix with complex eigenvalues?
It would be diagonalizable over complex numbers. Okay, so suppose you have a matrix A with complex eigenvalues, right? What would the corresponding D be? It would be a diagonal matrix with complex entries, right? That would not be a real matrix. Right? So it's diagonalizable, but it would be diagonalizable over the field of complex numbers. So typically, I think in your matrix theory course, you would have implicitly looked at diagonalizability over the complex numbers. Because if you work with complex numbers, then it's much easier to ensure diagonalizability. So going back to our original problem, suppose that A has repeated eigenvalues. Then how do we know if a matrix A is diagonalizable or not? Yep, so how many linearly independent eigenvectors do you need? Okay, so if you are able to find if we can find n linearly independent eigenvectors, then we're done. Right? So in particular, if you look at, so it's possible that a particular eigenvalue is repeated, right? So in other words, you take determinant of A minus lambda I. This has a number of roots. Some roots could be repeated. Maybe a particular root is repeated 3 times. Then for it to be diagonalizable, the eigenspace, that is the set of all eigenvectors corresponding to that particular eigenvalue, that should be a vector space of dimension 3. If it's any less than 3, then it means that this space is deficient, so the corresponding matrix A would not be diagonalizable. Alright. So if we are able to find n linearly independent eigenvectors, then we are done. In general, a matrix A is not diagonalizable. So let's look at a specific subclass of matrices for which we can say something. Alright, and that in fact turns out to be the set of all symmetric matrices. So a matrix A is symmetric if A equals A transpose. But symmetric matrices have some very nice properties. Firstly, symmetric matrices are always diagonalizable. In fact, they have an even nicer property. So suppose that I take any 2 eigenvectors, right, corresponding to A. Suppose that they correspond to different eigenvalues. So suppose that lambda 1 and lambda 2 are eigenvalues of some symmetric matrix A. Okay. Let us look at, suppose that V1 and V2 are corresponding eigenvectors. All right. Let me take V1 transpose A times V2. What can you say about this? What is A times V2? It is lambda 2 times V2, correct? So let's write that out. So it is V1 transpose times lambda 2 times V2, which is just lambda 2 times V1 transpose V2. Okay. Now I have V1 transpose V2. What is the transpose of this entire thing? Yep. So that would be V2 transpose A transpose V1, but A transpose is equal to A, right? It's a symmetric matrix. This is just equal to V2 transpose A times V1, right? So these two quantities are essentially the same, right? Because this is just a real number, so the transpose of a real number is itself. So this is equal to V2 transpose A times V1. But what is A times V1? It is lambda 1 times V1, which is lambda 1 times V1 transpose V2. V2 transpose V1 is the same as V1 transpose V2. So as it turns out, this quantity is equal to this quantity, but lambda 1 is not equal to lambda 2, that we know, right? So when can that happen? So it should be the case that V1 transpose V2 should be equal to 0. So it is not just, so if I look at any two distinct eigenvalues, then the corresponding eigenvectors are orthogonal to each other. And that is a particularly nice property of symmetric matrices. Symmetric matrices are not just diagonalizable, they're orthogonally diagonalizable. So you can find an orthonormal basis consisting purely of eigenvectors. Correct? So if a matrix is diagonalizable in general, then you can find a basis purely of eigenvalues. For symmetric matrices, you can find a basis of eigenvectors, but not just that, you can also find an orthonormal basis consisting purely of eigenvectors. All you have to do is normalize, right? So if V is an eigenvector, then any scaled version of V is also an eigenvector. So I could just normalize and ensure that every eigenvector has norm equal to 1. Correct? So what this implies that eigenvectors corresponding to orthogonal. What about eigenvectors corresponding to the same eigenvalue? Suppose that an eigenvalue is repeated. Okay, so I need to find two eigenvectors, two linearly independent eigenvectors to form a basis. correct, for this particular eigenspace. Can I always choose them to be orthogonal to each other? Can I choose them to be orthogonal to each other? So let me write that down. So suppose that lambda is a repeated right. So suppose that the arithmetic multiplicity which is simply the number of times the root repeats in the characteristic polynomial, this is equal to, let us say, 2. Okay, I know that the matrix A is diagonalizable, A is symmetric, therefore diagonalizable, and lambda is a repeated eigenvalue, it repeats twice, which means that I can find two linearly independent eigenvectors corresponding to lambda. Can I choose these two eigenvectors to be orthogonal to each other? So can we choose v1, v2 eigenvectors? You can't? Are you sure? Okay. How many say that you can't choose orthogonal, these eigenvectors to be orthogonal to each other? How many say it is not possible to choose orthogonal eigenvectors? How many say it is possible to choose orthogonal eigenvectors? Okay, if you think it is possible, why is it possible? Or if you think it's not possible, why is it? Can you give me an instance where it is not possible?
We can find an orthogonal vectors in the brain, but we need to make sure that those are also eigenvectors of them.
Correct, true. My claim is that you can. So suppose you are given a basis, right? So v1, v2 would form a basis for this particular eigenspace, correct? Question is, can I choose an orthogonal or orthonormal basis for this particular eigenspace? But
those are need not to be eigenvectors.
But that is by definition the eigenspace, right?
A1 is lambda v1.
Sorry, A?
A1 is lambda v1.
Okay.
And A2 is lambda v2.
Yep.
So v1 and v2 are eigenvectors. We subtract the two. Then we get v1 minus v2 is also an eigenvector with the same eigenvalue lambda.
Sure.
So from that we can now create three.
Okay.
In order to create two vectors out of three vectors in which one is linearly dependent on the other, which is v1 minus v2.
Agreed. Is there a more systematic way of doing this? Just Gram-Schmidt, right? So if you look at the set of all vectors v such that a times v equal to lambda times v, right? This forms a vector subspace, correct? So this is the set of all eigenvectors corresponding to the eigenvalue lambda, correct? So this is corresponding to the eigenvalue lambda, and this forms a vector space. Does everyone agree that this forms a vector space? I don't see any response. How do you argue that this forms a vector space? Do you need to verify all of those 7 properties? It's just closed under linear combinations. You take any set of eigenvectors, take a linear combination of those eigenvectors that will also give you another eigenvector. Right? So this forms a vector space if the matrix A is diagonalizable, then it's sure to form a vector space of dimension 2, because I'm saying that the arithmetic multiplicity is equal to 2. Right? So, which means that I can choose a basis consisting of 2 linearly independent eigenvectors. But if you can choose linearly independent eigenvectors, you can also choose orthogonal eigenvectors just by using Gram-Schmidt. Correct? And why is that still an eigenvector? Because ultimately you're just taking linear combinations. Right? How did you obtain the orthonormal basis from the original set of vectors? It is through some linear combinations of those vectors itself. Correct? So if you go back to right, in each of these cases, what kind of operations did you perform on V1, V2, V3 up to Vm in order to get U1, U2 up to Um? You only perform linear operations, right? In fact, you just took linear combinations of V1, V2, V3 up to Vm in order to get U1, U2 up to Um. But any linear combination of eigenvectors also gives you another eigenvector. Correct? So if I do Gram-Schmidt orthogonalization, then you end up with an orthonormal basis. Correct? So in fact, it's good to just take an example and work it out yourself. So let's just take a matrix. So, 1, 2, So anyway, I don't think I have a good example right now, but maybe I'll give that as an exercise. So an example of a 3 by 3 matrix which has a symmetric matrix which has repeated eigenvalues, and you will be able to find an orthonormal basis of eigenvectors for that particular matrix. Okay. So these are some nice properties of symmetric matrices. Correct? It's always diagonalizable, and in fact it is orthogonally diagonalizable. In fact, if a matrix is orthogonally diagonalizable, then it must be symmetric. Why is this the case?
The transpose
Okay,
transpose won't be able to raise equality.
which equality conditions?
Like when we did the other way around,
Okay,
like when A is symmetric, we get eigenvectors that are orthogonal to each other.
correct,
Now we are trying to prove its converse.
correct.
We
These orthogonal diagonal equal to transpose B into B.
Correct. So in fact, what do the eigenvectors? How do the eigenvectors relate to A equal to, say, P D P inverse? Correct. So if you can write A as P D P inverse, then the columns of P essentially are the eigenvectors. So in that case, what is P inverse equal to? So P transpose, because you can find an orthonormal basis, right? So A is in fact P D P transpose if A is orthogonally diagonalizable. But if that is the case, then what is A transpose equal to? P D P transpose, the whole transpose, which is just P D transpose P transpose, but D is a diagonal matrix, so this is just P D P transpose, right?
So what do we mean by orthogonally diagonal?
When I say it is orthogonally diagonalizable, it means that I can find a basis of orthonormal eigenvectors for A.
Sir, also find if we have a particular eigenvalue,
Correct.
then corresponding to that, can we have two independent eigenvectors corresponding to that single eigenvalue?
Yes, if the eigenvalue is repeated. Only if it is repeated. Right. Any questions? A specific subclass of symmetric matrices is the set of all positive semi-definite matrices. So we say that so if I have a matrix A which is symmetric, so we say that A is positive so it is positive semi-definite if all the eigenvalues of A are greater than or equal to 0. Because A is diagonalizable, it means that all the eigenvalues are real, but it's positive semi-definite if they're not just real, but they're also greater than or equal to 0. Okay. Again, just because they're symmetric, it also means that they're also orthogonally diagonalizable. Right. So the nice thing about these positive semi-definite matrices is that you can find, in fact, let's try to compute the largest eigenvalue of a positive semi-definite matrix A. Right? In fact, any matrix, in fact. So this turns out to be equal to the maximum overall V not equal to 0 of V transpose AV divided by V transpose V. So I can in fact find the largest eigenvalue of A by solving an optimization problem.
Norm of A, not norm. Below is norm of
Yeah, norm square of V.
norm square.
Yes.
Is the numerator like norm of A?
Would it be norm of A times V?
Like,
So suppose that V were actually an were equal to the largest eigenvalue. Sorry, if suppose V were the eigenvector corresponding to lambda, the lambda max, then what would the numerator be? So it's V transpose lambda V, so that's lambda times V transpose V divided by V transpose V, so it would be equal to lambda. Correct?
The symmetric matrix is orthogonal.
Correct. I can also write this particular equation as the maximum overall V such that norm of V equal to 1 of V transpose AB. Right. But why is this true? Let's see why this is true. Let us look at, take any vector V, right? So V lies in Rn, and we know that A is symmetric, it is positive semi-definite. So in other words, it's orthogonally diagonalizable, and we can form a basis, an orthonormal basis, purely out of its eigenvectors. Correct? So we can write, so let us say V1, V2 up to Vn are orthonormal eigenvectors of A. Correct? And each of these correspond to eigenvalues, and let us say that so these correspond to eigenvalues lambda 1 through lambda n, and let us say that lambda 1 is greater than or equal to lambda 2, and so on is greater than or equal to lambda n. We just order these eigenvalues in decreasing order and take the corresponding eigenvectors. Eigenvalues can be repeated, that is fine. Okay. So let us say that I express it in this particular form. Then I can write V as some linear combination of these VI's, because after all this forms a basis. So V is summation I equal to 1 to n, some alpha I VI. Now if V has unit norm, then what does that imply for on alpha I? Or in other words, what is the norm of V equal to? So, or in other words, what is V or norm of V squared equal to? it's equal to sum of alpha square, right? So this is equal to V transpose V, which is just summation I equal to 1 to n alpha I Vi transpose summation, let's say j equal to 1 to n alpha j Vj 1 to n summation j equal to 1 to n alpha I alpha j Vi Vj, sorry, Vi transpose Vj, but the Vi's are all orthonormal, right? So Vi transpose Vi equal to 1 and Vi transpose Vj equal to 0 for j not equal to I. So this just gives me summation I equal to 1 to n alpha I square. Okay, so let's keep that in mind and look at the following expression, V transpose A times V. So what is V transpose A times V equal to? What is A times V? So this is V transpose times A times summation I equal to 1 to n alpha I Vi, which is V transpose times summation I equal to 1 to n alpha I AVI, and that is just equal to, so it's V transpose summation I equal to 1 to n alpha I lambda I Vi, correct? So what will this be equal to? V transpose this, so summation I equal to 1 to, or summation j equal to 1 to n alpha j Vj transpose summation I equal to 1 to n alpha I lambda I Vi, which just turns out to be summation I equal to 1 to n alpha I square lambda. Right, so, and what do I know about the alpha i's? If V has unit norm, then summation I equal to 1 to n alpha I square is equal to 1, correct? So in fact I can write this as summation I equal to 1 to n beta I lambda I, where each of the beta i's is greater than or equal to 0 and the summation of all the beta i's is equal to 1. So for what choice of beta is this going to be maximized? Correct. So this will be maximized if you take beta equal to 1 for I equal to 1, right? So this is maximized by beta 1 equal to 1. because it's just a simple uh, convex combination of the lambda i's. Lambda 1 is the largest, right? So you can choose that to be the largest when it's maximized when you put all of the mass on lambda 1. So V transpose AV, the maximum, turns out to be equal to the largest eigenvalue. Okay, but this, I mean, in this we've made some particular assumptions. So if the matrix is symmetric, positive, semi-definite, then we can compute the largest eigenvalue in this particular. All right. So as I said, a positive semi-definite matrix is one for which all the eigenvalues are greater than or equal to 0. This in particular implies that V transpose AV for a positive semi-definite matrix what can I say about V transpose AV for any vector V? Okay, but I mean, in general, if all the eigenvalues are greater than or equal to 0, this quantity is always going to be greater than or equal to 0, right? And as you said, this is also going to be less than or equal to V transpose V times lambda max, right? And we say that a matrix is positive definite if all the eigenvalues are strictly greater than 0. Right? So why are we so interested in these positive semi-definite and positive definite matrices? As we'll see some examples later, but as it turns out, our goal is of course to solve optimization problems, right? And it turns out that the kind of optimization problems that we can solve are those for which the function, the objective function, is convex, and the set of constraints form a convex set. Now there are different ways of representing this, and there are different classes of convex optimization problems. Now among the various convex optimization problems, among the class of constraints that we can handle, a particular subset of constraint sets are of the following form: that some matrix A is PSD. So we'll be interested in, say, optimization problems of the following form, where let's say that we want to maximize, as we saw earlier, the log determinant of, let's say, I plus A. I'm giving a rather straightforward example, such that, and the maximization is performed over all matrices A which are PSD. Okay, so the set of constraints is that the matrix A should be PSD. I want to maximize this over all possible matrices A which are positive semi-definite. That is one kind of an optimization problem that we want to solve. So we want to be able to handle constraints not just of the form, let's say, f of x is greater than or equal to 0, or f of x is less than or equal to 0, but also constraints of this particular form, like A is positive semi-definite or A is positive definite. Right? That forms an interesting class of optimization problems itself, and as we'll see, this also forms a convex optimization. Okay. So some more notation, we'll say that so the set of all n by n PSD matrices we'll denote this by this S plus, and the set of all positive definite matrices we will denote this by S plus plus. So we'll come back to the set of positive semi-definite matrices again and again. But a basic property that you can prove is that the set of all positive semi-definite matrices is a closed set. And another nice property of positive semi-definite matrices is that they have a valid square root, right? Because we can write A as P D P transpose, and every entry of D is non-negative, right? So D equals lambda 1, lambda 2 up to lambda n. So if I look at d to the half, which is defined as square root of lambda 1, square root of lambda 2 up to square root of lambda n, and all the off diagonal entries equal to 0, then what can I say about P d to the half P transpose? If I multiply this matrix with itself, what do I get? P transpose d to the half P transpose. But what is this should be this P d to the half P transpose. What is P transpose P equal to? It is an identity matrix, right? Because P is an orthogonal matrix. So this is equal to P d to the half P transpose, or A. I'm sorry?
Can we generalize taking 1 by n? So not necessarily a square root, but
Correct, that is true. You can define a cube root, you can define and in general the nth, because it's not. Okay, and it has this particular property that that matrix whole to the power whatever k would be equal to A. So we refer to this particular matrix P d to the half P transpose, we call this the square root of A, simply because it has a property that if you take the square of this particular matrix, then you get back A. And if you recall, we used this particular property when we tried to derive the gradient of log determinant of a matrix. Any questions? Okay. So with this, we'll end our sort of review of linear algebra. We spent a fair bit of time just reviewing a lot of basic concepts. But now we'll look at convex sets, convex functions, and how do we actually define and solve convex optimization problems. Okay. So yes.
Then why P transpose into P is
So P is an orthogonal matrix, right? So the columns of P correspond to the eigenvectors of the matrix A. That's it. Okay. So let's now look at some basic definitions and properties of convex sets and different kinds of convex sets. So we'll first try to define a line in Rn. So how do you define a line that passes through two given points? Suppose I am given 2 points, U and V in Rn. Let's look at R2 first. How do you define the line that passes through two points? Let's say U1, U2, this is one point, and the other point is V1, V2. Any linear combination? Okay, let's go back to high school. So if like using the high school method, suppose you are given, maybe let's use slightly more familiar notation. I'm given 2 points, x1, y1 and x2, y2. What is the equation for a line that passes through x1, y1 and x2, y2? Yeah, so y minus y2 upon x minus x2 is equal to okay, so should this be y2 or y1? Yeah, fine. So it's y1 minus y2 divided by x1 minus x2, correct? I want to write this a little differently, right? I want an expression for x comma y in terms of all of these. Okay, so can you give me an expression for x comma y in terms of these parameters? X, y equal to so in fact, if I multiply and divide this, the numerator and the denominator, so if I multiply the numerator and denominator by any real number, let's say alpha, this remains unchanged, correct? So now if I say that alpha y minus y2 equal to y1 minus y2 and alpha x minus alpha x2 equal to x1 minus x2, then everything essentially remains unchanged, correct? Sorry, I want to do it slightly differently. I'll multiply and divide the right hand side by some constant 1 minus alpha for any real number alpha, right? As long as it is alpha is not equal to 1 in this particular case. W transpose X plus B, okay. Sure.
And B is the X2 there, or the bias.
Correct. I'll want to write it in a specific form. Okay. So let me know if this is not okay. So I can write x comma y as x2 comma y plus 1 minus alpha times x2 y2 x1 minus y1 x2 minus y2. So if some x comma y satisfies this, then I claim that it also satisfies this particular equation. Do you agree with that point? Right. So, for example, if I fix some particular numbers, let me take 1 comma 2 and 2 comma 3, right? What is the straight line passing through these 2 points correspond to? So I have 1 comma 2, this is my u, and 2 comma 3 is somewhere here. This is my v. So the straight line passing through these 2 points should be something like this. But I claim that I can also, any point x comma y on this straight line can be written as, let's say, 1 comma 2 plus 1 minus alpha times 2 minus 1, 3 minus 2. Yeah. X1 I think here it should have been x1 minus x2 and y1 minus y2. So what is the slope of this particular line? 1, right? So let's look at the set of all points x comma y satisfying 1 such that x y equal to 1 2 plus 1 minus alpha times 1 comma 1. What is the slope of this particular line? So if I look at any y by x, what will that be equal to? Yeah, sorry, I should say not y by x, but the slope of this. So this will also be a line. If I take x comma y minus 1 comma 2, then that will be a straight line passing through the origin, and the corresponding slope will also be equal to 1. It's equal to this divided by this particular quantity. Correct? So you can think of this this particular equation, you can interpret it in the following form. I take a particular point 1 comma 2 and then I move along the direction of 1 comma 1, right, by an amount 1 minus alpha for any alpha in R. If alpha is, let's say, less than 1, then you move in the direction of 1 comma 1. But if not, you move in the opposite direction. So you start with a particular u, and v minus u gives you some particular direction, correct? So you can write any vector, let me call this vector x, to be equal to u plus some quantity, I'm just using 1 minus alpha, times v minus u. So if this quantity is always positive, then it basically corresponds to the ray shooting in this direction. If this quantity is negative, then it means that it's a ray shooting in this particular direction. Okay, but this is of course in 2 dimensions. We got this intuition from 2 dimensions, but in fact it can be generalized to any n dimension. So I write it in this particular form because I can rearrange the terms a bit. So if I take out all the terms corresponding to u, I get u plus 1 minus alpha or minus 1 minus alpha times u. So this is just alpha times u plus 1 minus alpha times v, where alpha is an arbitrary real number, not constrained to be, let's say, between 0 and 1, right? So if I take any 2 points u and v, then the straight line passing through u and v, this is equal to the set of all alpha u plus 1 minus alpha v for alpha in R. Right? If you're still not convinced, just take these 2 examples, compute the set of all alpha times 1 comma 2 plus 1 minus alpha times 2 comma 3 for different values of alpha, and you'll see that it all lies on a straight line. Okay, so this is a straight line, but if I restrict alpha to be only between let's say 0 and 1, then what would I get? I would just get this line segment that joins u and v. So the set of all alpha u plus 1 minus alpha v for alpha being between 0 comma 1, this is just the line segment joining u and v. So we'll say that a set is convex if you take any 2 particular points, then the straight line, the line segment joining those 2 points also lies within this particular set. So we say that a set A is convex if uv belongs to A implies that alpha u plus 1 minus alpha v also belongs to A for all alpha in 0 to 1. Right, so I take an arbitrary set. So this set would not be convex because I can take a point over here and a point over here. If I take the line segment joining these 2 points, this does not lie, a part of this line segment lies outside this particular set. So this is not a convex set, right? But on the other hand, if I drew, let's say, a circle, then this would be a convex set because no matter which 2 points you take inside the circle, the line segment joining those two is fully contained within this particular circle. Okay, so maybe let's stop here. Any questions? Yeah? Okay, you tell me, would it be considered convex? So you draw a square. Do you think it is possible to draw a line segment which lies strictly outside the set? So assuming that when you say the square, you're also including its boundaries, right? So it's the square with the edges. So in that case, it's no matter which 2 points you take inside the square, the line segment joining those 2 points is always contained within the square. We'll see that this is also a special type of a convex set. It's in fact a polyhedron, polytope, as we'll see. So let's stop here if there are no other questions.